Welcome to Lesson 20. In this session, we'll look at some number processing, which gives most people a lot of difficulty. Dividing large numbers is something people are just not comfortable with. As always in maths, we begin by breaking the task down into simpler steps. So when confronted with the task, 3,712 divided by 15, we break up the larger number into more manageable pieces, as Miss Gloria will demonstrate.
"37 divided by 15 is 2. This shows that 2 times 15 accounts for 30 of the original number. We still have 7 unaccounted for, so we combine that with the next part of the original number, that is the 1. So we restart the division process with 71. How many 15s fit into 71? That answer is 4. Multiplying 15 by the blue 4 gives the blue 60. The 11 represents what is unaccounted for at this stage. We combine that with the last part of the original number, the 2. We repeat our 3-step process for a final time. 112 divided by 15 is 7. 7 multiplied by 15 gives the green 105. Our final subtraction leads to the number 7, which is called the remainder. It is written as the top of the fraction in the final answer. Our complete working looks like this. Your answer is correct. Well done.
That is the most common approach to what's referred to as long division. Because people find it so difficult, we'll do another example. This one will use slightly bigger numbers. Now, when we look at the task, here's the number we are dividing by, and this is the big number. So we want to know how many of these are there in this number. How many of these do you need to make this? Now, we make the task simpler. We take the first 2 digits, so we're effectively looking at 9,200. But the way we view it, how many 62s are there in 92? And we know that we can extract only 162 from the 92, and we write that in our working here. It means that in 9,224, we know we have at least 100 of the 62s. Now, there may be more. So what's not accounted for is 3,024. We want to know how many of the 62s are in what is unaccounted for from the original value. So we express this calculation as a second component of our total solution. Now notice the presence of the zeros. These indicate the actual values, but we only investigate how many 62s are in 3,020 by looking at how many 62s would be in 302. Now we don't usually include these zeros. It allows us to save some time. So think about that as Miss Gloria takes you through the full calculation.
$9,224 is too big to work with in one piece. So we trim it to the smallest number bigger than 62. This is 92. 92 divided by 62 is 1. This shows that 1 times 62 accounts for 62 of the original number. We still have 30 unaccounted for, so we combine that with the next part of the original number, that is the 2. So we restart the division process with 302. How many 62s fit into 302? That answer is 4. Multiplying 62 by the blue 4 gives the blue 248. The 54 represents what is unaccounted for at this stage. We combine that with the last part of the original number, the 4. We repeat our 3-step process for a final time. 544 divided by 62 is 8. 8 multiplied by 62 gives the green 496. Our final subtraction leads to the number 48, which is called the remainder. It is written as the top of the fraction in the final answer. Our complete working looks like this. Your answer is correct. Well done.
The next example introduces what some people find to be a significant complication. Look closely at the blue working in the middle of the calculation. Think carefully about it, because this aspect often leads to student errors.
$8,529 is too big to work with in one piece. So we trim it to the smallest number bigger than 78. This is 85. 85 divided by 78 is 1. This shows that 1 times 78 accounts for 78 of the original number. We still have 7 unaccounted for, so we combine that with the next part of the original number, that is the 2. So we restart the division process with 72. How many 78s fit into 72? That answer is 0. Multiplying 78 by the blue 0 gives the blue 0. The 72 represents what is unaccounted for at this stage. We combine that with the last part of the original number, the 9. We repeat our 3-step process for a final time. 729 divided by 78 is 9. 9 multiplied by 78 gives the green 702. Our final subtraction leads to the number 27, which is called the remainder. It is written as the top of the fraction in the final answer. Our complete working looks like this. Your answer is correct. Well done.
The last and final example introduces a new aspect. The number we're dividing by is larger than the first two digits we normally process. Watch how this is handled.
When we look at this problem, we see that 82 is bigger than the first two digits of 6,663. So we trim the big number to 666. 666 contains 8 of the 82's. This accounts for 656. So it leaves 10 unaccounted for. We combine it with the 3 from the end of the original number. Now we move into our final division step. 103 divided by 82 is 1. Our blue total is 82. This leaves 21. We have used all the digits from the original number, so the calculation is finished. And 21 is the remainder. Our complete working looks like this.
So for our conclusion, in each of the 4 examples, the division process proceeded by breaking up the original problem into a set of smaller calculations, each of which applied exactly the same logic. Once again, we have an algorithm at work. Find the small process and apply it repeatedly. Well, that will do for this topic. I hope to see you in the next lesson. See you then.